Welcome to this video. In our previous videos, we explored evaluation metrics for classification problems, precision, recall, F1 score, FPR, and also ROC and PR curve. And we learned how to measure how good a classifier really is. But what happens when the output is not a class, but a number? Today, we're stepping into the world of regression. And I'm going to introduce you to two very important personalities, the punisher and the forgiver. One of them heavily punishes large errors. The other one is more forgiving. These are not superheroes. These are regression metrics. We'll break down RMSE and MAE in a way that actually makes intuitive sense. And by the end of this video, you'll also understand R2, a metric that, in many ways, plays a role similar to F1 score in classification. Let's dive in.
When working with regression problems, that is, problems that involve estimating a continuous value, the most commonly used error measures are RMSE, root mean squared error, and MAE, mean absolute error. The distance between what your model said would happen and what actually happened is called the error. And how we decide to measure it? Well, that changes everything. Alright, let's start with a metric that takes a really hard line on mistakes. This is what I like to call the path of the punisher, root mean squared error, or as you'll always see it, RMSE. But hang on, before we can even get to the R and RMSE, we have to start with its foundation, which is mean squared error, or MSE. It's pretty simple, really. For every single prediction, you calculate the error, and then you square it. And once you've done that, for all your data points, you just take the average. That's it. And that squaring step, that's the whole philosophy right there. An error of 2 becomes 4. No big deal. But an error of 10, that becomes 100. This little trick makes your model absolutely obsessed with avoiding those big, embarrassing mistakes. Now, the only weird thing with MSE is that your units get all messed up. They're squared. You end up with things like square dollars or square degrees. It's not super intuitive. So we do one last simple thing. We take the square root of the MSE to get our RMSE. That brings the error value right back down to the same scale as what we were trying to predict in the first place, making it way easier to understand. Okay, but what if you don't want to punish those big errors so harshly? Well, that brings us to our second path, a much more forgiving philosophy, using mean absolute error, or MAE. The name pretty much says it all, right? Instead of squaring the errors, we just take their absolute value, to make them all positive, and then we find the average. It's a much more direct, straightforward way to measure your typical error. See, there's no squaring going on here to amplify the big mistakes. An error of 10 is just twice as bad as an error of 5. Plain and simple, this linear approach makes MAE much less sensitive to those crazy outliers. A few wild predictions aren't going to completely tank your final score. So let's imagine our model made 5 predictions. Most of the errors are pretty small, right? A 2, a -3, a 1, a 4. But then there's one massive miss. A huge outlier error of -20. And trust me, this kind of thing happens all the time with real-world data. So now check out what happens when RMSE gets a look at these errors. The small errors, yeah, they stay pretty small. 4, 9, 1, 16. But that -20 outlier squaring, it turns it into a colossal 400. It now completely dwarfs all the other errors combined. It's basically the only thing the metric sees. And here's the crucial point, the real takeaway. When you tell your model to minimize RMSE, you are actually teaching it to predict the mean of your target values. Because the mean is super sensitive to outliers. But when you minimize MAE, you're teaching it to predict the median, which is way more robust to those extreme values.
Okay, we've measured our error, but how do you know if that error is actually good or bad? We need a referee. An RMSE of 100 is amazing for a house, but a total disaster for a cup of coffee. Context is everything. This is where R² steps in. It's a relative metric that compares your fancy model to a dumb one. It asks, how much better are you than a model that does nothing but predict the average value every single time? You get a score between 0 and 1. 0 means you're no better than guessing. 1 means you're flawless. So a 0.75 tells you that your model successfully explains 75% of the variance in your data. It's your model's referee.
To compute R², which is similar to the F1 score, in the sense that it summarizes the performance of a regression model using a single number. We compare the model's error to the total variation in the data. Suppose the vector of true values is given as follows. The vector of predictions from our regression model is given as follows, and the mean of the data is defined as follows. In this case, if we divide the sum of squared prediction errors by the total sum of squares, which represents the variance of the data, we obtain this quantity, 1 minus r squared. This equation can also be written as follows. In practice, r squared can be interpreted in three main cases. In the best case, if the model predictions are exactly equal to the true values, the error becomes 0, and r squared equals 1. This means the model explains all the variation in the data. If the model has learned nothing useful and predicts the mean value for all samples, the model error equals the total variation in the data, and r squared equals 0. This means the model performs no better than predicting the mean. In the worst case, if the model predictions are even worse than predicting the mean, the prediction error becomes larger than the total variation. In this situation, r becomes negative, indicating that the model performs poorly.
Thank you for staying with me all the way to the end. If you found this video helpful, please support me by sharing it with your friends and anyone who loves AI and machine learning. Don't forget to subscribe to the channel and feel free to share your thoughts and ideas in the comments. I'd love to hear from you.